Hellwig team.
Hi, I'm Brady.
I'm Luke.
I'm Daniel.
I'm Caitlin.
And this was our project, the Linear Motion Electrical Contact Test Stand for Hellwig Carbon Products. Hellwig Carbon Products is a company that specializes in brush fabrication using graphite and carbon as matrix material. These carbon brushes are electrical mechanical pieces that take electricity from a moving surface and transfer it to a stationary conductor. There are multiple applications that vary from motor commutators to large gantry systems. They offer multiple brush material, shapes, and force application assemblies. Our problem statement was that Hellwig Carbon Products Milwaukee does not currently have a way to test the mechanical and electrical wear of their metallic graphite brushes under linear motion with controlled conditions. Here we see one example of the way that the carbon brush would be used, which is in mining applications. And here we see the carbon brush in contact with the V-shaped rail. So this is our overall system design. So to get some vocabulary out of the way, we have the electrified rails hanging down from the top of the test stand. Underneath that, we have the sled, which is in charge of pushing the carbon brushes into those electrified rails. The sled slides along a drive system, which will slide across the rail, creating a friction, which will create that mechanical wear. The rails are electrified, which will create the electrical wear. There is data acquisition equipment both on the end of the test stand and on the sled, which will help get the readings for how the carbon brush is performing. This is the carbon brush that we are testing, and it will be pushed up like that into the V-shaped rail. To complete our project, we created overall objectives and constraints. So the constraints that we must achieve that shall be able to be broken down and transported from the MSOE Hall of Science and then reconstructed at Hellwig Carbon Products. The overall system should not be longer than 16 feet, wider than 5 feet, taller than 7.5 feet, and should not exceed a weight of 2,000 pounds. It shall include 2 rails, one positively charged and one negatively charged, and it shall provide 1 volt, 800 amps to the rail. This is a quick diagram of how that works. It shall have access from 3 sides and shall not exceed a budget of $20,000. The objectives we hope to achieve is that it should be compatible with different rail geometries, should be able to complete 10,000 continuous cycles, and should have easy access to the brush and brush holders. To complete the project, we broke it down to 4 sub-assemblies. Luke was in charge of the test stand structure and the electrical isolation. Daniel was in charge of the linear drive system. I was in charge of the sled assembly, and Caitlin was in charge of data acquisition and the power supply.
For the test stand and electrical isolation, some important objectives and constraints to consider is that the construction needs to be modular in design to allow for transportation from the MSOE Hall of Science to the Hellwig production plant. We also needed to place the sled at table height for comfortable work for the operators, and isolate the rails from the test stand frame so that there was no current loss due to the electricity converting to the test ring. We also need to enclose the actuator, rails, and sled to prevent injury to operators. So for the material selection, we decided to look into 3 different materials. We looked at the 80-20 aluminum extrusion, low carbon steel square tubing, and a 60-61 aluminum square tubing. The trade-off selection for these materials considered the weight per inch, the yield strength of the materials, the cost per piece, and the required modification for each material. And the winning material was aluminum 80-20 extrusion, which excelled at being modular in design so how we can later modify this project if they want to, and also the cost per piece to reduce our costs for the overall budget. So an overview of the system, the test stand is broken into 3 parts. We have the workstation and data collection section. This area includes the motor, the control cabinet, and the brake resistor, and it also includes the ammeters and voltmeters for the carbon brush current and voltage sensor. And then we also have a flat work area where a laptop can be used and an operator can collect data. And then we have the rail and actuator section. The test frame in this area can be broken into 2 sections for transportation. And it includes both electrified rails with the sled and linear actuator underneath, and then the rail connectors with 2 per rail above to isolate the rails from the frame. And then underneath is the machine base, which is vibrationally damped using vibrationally damping magnetic mounts. And it also includes a shelf where the power supply for the rails is placed. And the maximum weight is 1,880 pounds approximately. So from the front view, here you can see that the ammeter and the voltmeter are elevated to reduce the wire length to the carbon brushes. And then we also have the VIN hub and deck for easy access to collect data from a computer. And then we have the sled in the center unobstructed for the linear actuator with proximity sensors to allow it to move from one end to the other and for us to change the motion. And then next slide here, we can see that we have polycarbonate paneling around the actuator, the rails, and the sled. And this paneling can be slid into the sides as well as bolted on top and on the ends so that operators do not accidentally touch the electrified rails or obstruct the sled during operation. And we can also see emergency stops are placed at either end so that the operator can stop the machine if a malfunction occurs.
All right, so I'll be introducing the linear motion drive system that must be capable of achieving a maximum velocity of 5.6 meters per second for 75% of the total electrified rail length. Currently, the electrified rails measure 12 feet, so 75% of that is approximately 9 feet. Great. Before I dive into our design process of the drive system concepts, I just want to give the room a little bit more context as to what our application dynamics actually look like. And to do that, I'll just start off by showing a conventional trapezoidal velocity profile, assuming symmetrical acceleration and deceleration for one cycle. The linear acceleration the sled requires to achieve that top speed at the desired distance is 32 meters per second squared, or 3 Gs of acceleration. However, this assumes that there's an instantaneous change in acceleration, which implies that there's an infinite amount of jerk. And if you don't know what jerk is, it is the rate of change in acceleration. And this can cause issues such as structural resonances, as well as belt stretch if we're using like a belt actuating system, especially at these higher speeds. So most high performance systems, such as this one, use S-curve velocity profiles, where it basically ramps up the acceleration value, but it does so in a way where the drive mechanism accelerates more smoothly so that the actuating system experiences less mechanical shocks. Keep in mind that the values that you see on to the right are for the most extreme case scenario where we're considering 100% jerk limitation, which means very little to no mechanical shocks. Now that we know our dynamic requirements, we can now base our initial design concepts based on satisfying those requirements. And the first design concept is a custom belt actuator that uses a timing belt and timing pulleys of our selection. The second design concept is an off-the-shelf Misumi belt actuator that is directly coupled to an AC servo motor. The third design concept is a rodless pneumatic actuator provided from Parker. And the fourth design concept is a Beckhoff linear servo motor assembly, which uses a magnetic track to propel the linear motor from one end to another. To select the proper drive system mechanism, we created a down selection matrix that ranked these concepts based on specific categories such as speed, thrust capability, ease of integration, etc. Among the evaluated concepts, the Misumi belt actuator had the highest overall weighted score of 71 points, which indicates that it had the best overall balance between dynamic capabilities as well as project feasibility. Unlike the custom belt actuator, the Misumi off-the-shelf solution benefits from using standardized industrial parts, meaning that there's less risk of increased lead time and design effort needed to create a successful linear motion test stand. In other words, it can be said with confidence that a Misumi belt actuator can achieve these extreme dynamic requirements, while a custom belt actuator will need to undergo rigorous amounts of testing and prototyping before we even think about releasing it to Hellwig. While the pneumatic actuator and linear servo assemblies require a bit more of a complex setup, which makes integration a little bit more difficult. So jumping into our current design, what actually drives the actuator itself is a Beckhoff medium inertia AC servo motor. This was selected due to its high torque capability, even at higher speeds, as well as its exceptional closed loop feedback control using a high resolution encoder. To fix the motor onto the test stand structure itself, we'll need to make a custom motor mounting bracket that will be machined from 6061 aluminum L channels provided from McMaster or Speedy Metals. The motor itself will be directly coupled to an exposed pulley shaft using a high torsional stiffness servo disc coupler, and this avoids the additional maintenance and dynamic complexities that gearboxes might introduce. And to finalize this slide summarizes our motor sizing analysis for the current drive system. And due to time constraints, I can't really explain the dynamic model of the actuating system, but just know that we calculated the acceleration torque as well as the RMS torque for the motor. And then we validated whether the current selected motor can actually achieve that velocity profile using simulation tools that Beckhoff provided to us. So pretty much to ensure proper motor reliability, that RMS torque rating, which is that blue dot that you see on the graph, must be below that green line, which is your continuous motor torque rating, as well as within the red voltage boundary, which is your stall torque at 480 volts AC. As long as that blue dot satisfies both of those constraints, then this motor is properly sized for this application, and there's very little risk of it overheating during operation.
So for the sled assembly, the sled must have an adjustable contact pressure from the carbon brush to the rail of 6 to 16 psi. It also must safely secure the instrumentation on it and the carbon brushes. And the mass must be at most 20 kilograms. So the most important design consideration was how we were going to create this pressure and how we were going to adjust it. 3 main ideas were considered. First was to use tension springs to create a moment force, which would push the carbon brush up into the rail. 2 ideas were to decide on how to anchor that spring. First one was a connection piece that fit into slots. That you change which slot it was to change the length of this tension spring, change the amount of force. The second idea was to use an eye bolt, which as it turns would change the length of the spring. The next idea was a compression spring with a rack and pinion jack. The idea was you would have a dial that would change the height of this platform the compression spring is connected to. And then as that height changes, the length of the compression spring changes, changing the amount of force between the carbon brush and the rail. The last idea was again to create moments using a servo motor's torque. These were then organized into a Q matrix, which considered the cost, the ease of the pressure change, the mass, and the reliability. Reliability was considered the most weighted on this Q matrix because if this system fails, it could ruin an entire test or potentially cause safety issues for the operator. Cost was the lowest weighted because in any design concept, it came out to a lower cost than any of the other subsystems. The tension spring with the eye bolt came out to be the best option at 60 total points. This idea underwent many changes as we developed it during the design process. Here you can see we have a carbon brush sitting on top of an insulator. The insulator protects an S load cell, which measures the amount of force between the carbon brush and the rail. This is on top of an arm, which is pulled by a tension spring, which is anchored to a lead screw adjustment system. The base plate of the sled has various sensors on it. The S load cell is connected to a slotted joint on top of the arm. This ensures that the carbon brush will be perfectly aligned to the rail. There's a bolt used for the connection point for the springs onto the arm, and then there is a fall block, which prevents the arm from rotating to a horizontal position. This will aid setup when you are adding in the tension springs and will prevent it from falling and damaging the carbon brush in case of failure. This is a closer view at the lead screw adjustment system. The tension spring will be connected to these eye nuts, which are on top of a plastic connection piece on a lead screw. The lead screw, as it turns, will slide in and out of these 2 end blocks. Motion is prohibited to create bounds at the pressures that are needed. This is done when the plastic connection piece touches the end blocks. Then we also have partially threaded bolts going through the plastic connection piece that act as guide rails to prevent it from rotating as the lead screw turns. To decide how much force the tension spring needs to exert, I created this free body diagram based on the arm of the sled. The free body, the most important variables of the free body diagram are the applied force, Fa, which is how much force is between the carbon brush and the rail, and the spring force, Fs, which is the combined force of 2 tension springs. Using the equilibrium of moments, I was able to create this equation for pressure over where A is the contact pressure between the carbon brush and the rail. Using this equation, I was able to create this MATLAB graph, which plots pressure as a function of the spring length. Once I have this graph, I was able to use triangle geometry to figure out how far away the spring anchor point needed to be from its connection point on the arm to create the pressure needed for this project.
For data acquisition and power supply, there are a few diagnostics that were required. Starting off, we needed force contact sensors for each of the carbon brushes. Then we also needed temperature sensors in order to gather data of the temperature of the carbon brushes. Typically, this reaches a max of 200 degrees Celsius. Then we needed a vibrational reading sensor. This is to record the vibrations of the sled so we can eventually determine what would be a dangerous level of vibration to use the emergency stop to stop the system. Then, in addition to this, we needed to gather continuous current and voltage drop of the system itself. So for each sensor, what we ended up using was the Pew matrix to do our trade-off study. What you see on the screen here is our thermal diagnostics temperature sensors. We compared the thermocouple K-type to the infrared temperature sensor. These were based off of the accuracy, cost, the way it could be mounted, as well as the measurement style, such as if it was contact or contactless. Ultimately, for this Pew matrix, thermocouple ended up being best for our design. Using the Pew matrices for each of the sensors, we developed the initial selection for data acquisition and the power supply. For the force sensors, we ended up selecting the S-type load cell. Then for the temperature sensors, as mentioned previously, we selected the K-type thermocouple. For the vibration sensor, we selected an accelerometer. For the current sensor, we selected a Hall effect sensor, which was rated to 0 to 200 amps. We plan to put 5 of these in parallel in order to capture those 800 amps for the system. Then for the voltage sensor, we have the 1 volt input voltage sensor. For the microcontroller, we selected a vent hub. For the switch sensor, we selected an infrared beam break proximity sensor. For the rail power supply, we are using a high current electroplating rectifier that can supply 0 to 6 volts of DC power to 0 to 1,000 amps. And for the external power supply, this is what will be used for the sensors. Any of the sensors that needed 5 volts will be running off of the computer USB power supply. And then anything beyond that is running off of the 24-volt DC 1 amp power supply. For the wiring diagram of instrumentation on the sled, as you can see on the sled base here, we have the accelerometer, Wheatstone bridge, thermocouple DAC. These will all be connected to the vent hub, which is then connected through a wire to the computer USB port. For each of the sled arms, we will have one S load cell, as we showed earlier in the presentation, and then we'll have the thermocouples poured into the carbon brushes in order to gather the temperature data. For the wiring diagram to detect sled at each end of the rail, we have a 24-volt power supply that is hooked up to 2 proximity sensors. These sensors have an emitter and receiver, and as the sled passes through the emitter and receiver, breaking the beam, this will indicate when to start deceleration of the sled and change the direction of motion. Now for the wiring diagram of the power rails, ammeters, and voltage sensors, what we've developed here is we would use the rail power supply. This will connect with cable wires to rail 1, which is in contact with the first carbon brush. From the carbon brush and tail, it will go from the carbon brush back to the first ammeter, from the first ammeter to the second carbon brush, which is in contact to the second rail, to the second ammeter, which will then be back grounded to the power supply. For each ammeter system, we'll have the voltage sensors there as well, and then everything will be hooked up into the input DAC or the vent hub, which will then be relayed back to the computer USB port. Now, just to give a little bit more context on this ammeter design that we came up with, what we have here is a copper bus bar ammeter. So here, this copper bus bar is rated to be able to withstand up to 1,000 amps. There'll be the copper bar conductor placed between the 2 bus bars, and then they will be slotted through the Hall effect sensors. And then we have insulators to ensure that the test stand itself does not have any current flowing through it.
For the upcoming semester, we plan to resize the sled. This will allow us to put more sensors on the sled and not on the test stand. This will help us reduce wiring and reduce costs. We want to further study the effect of sled mass on the motor sizing in case Hellwig wants to add to the sled mass. We want to redesign the rail connector to include a clamp that can be used for various rail geometries. We also want to partially redesign the structure to allow for rail removal from the front or back instead of on the sides. And we also want to reduce the weight of the overall test stand. We want to move the rails power supply from underneath the machine base over onto the top, which will also help reduce wiring and reduce costs. We want to perform a static structural analysis on critical frame members and a vibrational analysis on the entire test stand. Our electrical cabinet is currently NEMA 1, and we want to upgrade that to NEMA 4. The difference is that NEMA 4 is sealed, which will help prevent conductive carbon dust from coming off the carbon brushes onto our electronic equipment and destroying them. We want to have the team get machine shop training to prepare for the construction and then start preliminary construction of the test stand, sled, and drive system here at MSOE before finishing construction at Hellwig, where we will perform testing and wire the rails. Our overall bill of materials came out to about $31,000, which is about $11,000 over our initial budget. This budget has been submitted to Hellwig and is currently under review. We also want to thank our Hellwig corporate sponsor and specifically the people that we've worked with at Hellwig, being David, Nitin, Randy, Andrew, and Dan. On a side note, we also want to thank our academic advisor, Dr. Hart, for helping us every step of the design process. Any questions?
Cool. Okay, thanks, guys. All right, we got about 7 minutes for questions. Industry first, then committee, then general.
I guess what was your biggest challenge on this project?
I would say the biggest challenge is going from theory to actual design. Throughout school, you're taught a lot of convergent thinking. You're given the problem, all its parameters, you have to get down to a single answer. In this problem, we were given a problem and we had to think of as many ways to solve it and then develop those ideas to figure out what worked and what didn't work. And it's very different from the environment we're used to working.
On behalf of working with the power supply, I would say that it was quite difficult just gathering resources to understand, okay, what kind of cable wires are we going to need? Taking into account, we started off looking at sensors and then what would work for the application versus like what's actually driving the cost. So starting off, I was looking at sensors being like, okay, we're trying to minimize the cost, right? We're looking to try and fit the budget, as we already knew in some departments it was already getting pretty high. And then as soon as we started adding in the wiring, we we're like, oh my goodness, this is getting higher.
Yeah.
So taking all that into account was a lot.
Yeah, and for the drive system, I mean, it's very difficult to try to figure out designing what is essentially a railgun. But I think my biggest challenge with the drive system is trying to optimize the cost as much as possible. The reason we went with the Masumi belt actuator is because it has like an open bearing design. Well, like a lot of like belt actuators have like enclosed bearing designs, but the actuator alone for those designs are like well over like half the budget cost.
Luke, want to chime in here?
Yeah, I can chime in, yes. I think bringing something up best is like actually actualizing the project and especially with the budget and making sure to how are we going to build this thing? How are we actually going to connect everything? How all these little details work together, especially as work on the test stand, you have to make sure everything could actually fit onto the piece and how we're going to connect everything and how much it's actually going to end up costing. So just researching real world products and figuring out what can actually work on our product is definitely a difficult thing. It's something new to work on, just haven't been used to.
Any other questions from industry sponsors? Don't want to give them the business right now.
Okay, committee members, Mike, do you have any questions?
Yeah, just a brief one. This project, I think all of your mechanical engineers have a lot of electrical components, a lot of things that are probably outside of what you've been trained in. How did you go about learning and approaching all this new material?
So the big thing is asking for advice. We tried to get into contact with professors that were from different departments that had a little more information. And we also got into contact with people who are studying other majors such as electrical engineering, and then a lot of internet research.
And Randy.
Yeah.
Anything else from you?
Maybe just one out of curiosity. So I saw that it has to last 10,000 cycles. Is that one test? Or is that just the lifespan of the whole test apparatus before parts would need to be replaced?
Yeah, that's one.
That's 110, okay.
Yeah.
How long does that last?
Well, currently, I don't have any dwell time implemented in the drive system, so like a pause time at the end of each cycle. But with the speed that we're going right now, like back and forth, it's going to approximately take like 2 hours and 30 minutes.
Okay.
Yeah, but if we add like, I don't know, a couple of seconds of pause time just to make sure we're not melting anything, that's probably gonna go on for like 3 hours.
Yeah, that's not max speed. Okay.
If it makes you feel more comfortable, also in the back off simulation software, we did a thermal utilization percentage of the motor, and like we're at like 30%, so like we're well under, or we're well within the motor operation limit for 10,000 cycles.
1,000 amps is also the maximum. Okay, so, good. Running different amp ratings.
Okay, general audience, are there any questions from the general audience about the project? Come on, Dave.
Just
Oh, you want me to give you a hard ball? You want me to give you one? Nah, I'm just letting you. All right, good job, guys. Thank you.
That's good. See you later. Thank you, guys. Yeah.
Okay, a couple minutes of changeover. We're gonna stick to the schedule, so we'll start right at 2 o'clock for the next group, okay? See you later.
Thanks for everything, right?
All right. Yeah, I'll keep that out.
Okay.
I'll be just.
Yeah, it's nice to have your help, especially when we build it. Yeah.
Oh, yeah.
Gentlemen. Hello, sir.
You're eating again. You were just eating when I saw you were.
I know, man. I'm just trying to get in when I can. Busy day for me. I'm just trying to get a couple bites in when I can, you know.
Get like the gram of protein, body weight, and
I got it.
body weight.
Is this it for the semester today?
No, this semester, yeah.
Class-wise and all that stuff?
Yeah.
Yeah,
So most of the finals happen this week, Monday through Thursday,
this week that we just ended.
that we just ended, yep. So this Friday is like, kind of, I think, the last thing that any of you guys would have, right?
Yeah.
And then you're off to the bar. I mean, to Christmas holiday.
See, I see nervous laughter up there.
That means that I hit something accurate there. Where are we going, brothers? Yeah, they have price wings today or something. Not that I would know.
Never been there.
Yeah. What are you guys doing?
Good. We're got 10 of our 11 race dates now.
Okay.
Pretty settled, I would say.
Yeah.
At least a lot of verbal confirmations. I actually speak some paper right here. There's another signed signature page for Wauwatosa, which is good.
Nice.
Bunch of new venues this year. We're still searching for a title sponsor, so MSOE. He's the real deal.
Good luck with that one. We're trying to raise our own money. We're building a science building over there. New building.
This is nothing compared to the cost of the science.
Well, yeah, of course.
No, anyway, we are. A Quick Trip has left us, so they're still with us. They're still with us as an in-kind sponsor.
Yeah.
But so that name up on the top of the button up there, whatever you call it, the medallion, it's gonna disappear.
Oh, no.
We're going into the new year.
Well, what is the sponsorship set you back if you are so inclined?
If we got what we wanted, it'd be somewhere between 75 and 100,000.
Okay.
But the most we've ever got from any title sponsor was 70.
Okay.
So,
I'll see if there's any banks available for robbing and I'll get back to you.
yeah, great. US Bank to get started.
Yeah, okay, there you go. Is that your bank?
No, but they're one that's interested in becoming a sponsor.
Oh, okay. Why would I want to rob them then?
Well, you could help them get some of this money out of
There you go.
the till.
Yeah.
Start early, right? Getting that first year.
Yeah.
So, anyway,
All right, well, it is 1:59, so I think we can go ahead and green light to get started. So, two talks kind of related to the same topic, so we'll let you guys go ahead and get started.
Thank you for coming. Welcome, everyone. Today, we're going to be covering the Tour of America's Dairyland Barrier Shield. I'm Jacob Koziel. That's Charles May. We have Bjorn Fossen and Logan Chu. Our advisor is Michael Spear, and our client is Tour of America Dairyland. So just a little bit of the roadmap that you can look forward to in this presentation. It's kind of gonna be in the style of a crit race where it's only gonna take 20 minutes, but don't worry, there's not gonna be any crashing this time.
is there gonna be a winner though?
We're all gonna be winners by the end of this. We're gonna begin with the project motivations and problems, move to a little bit of background and existing solutions. We're gonna follow up with some requirements and design processes. We're gonna take a turn, go into competing concepts, final barrier design, FEA approach, impact and loading, as well as some project plan for semester 2, budget, summary, and as well as next steps. So it's a little bit of motivation and the client needs. So Tour of America Dairyland runs a really tight city street crit race for bikes. So riders are really close to curbs as well as their fans that are cheering them on. Right now, they use steel fences that have a lot of sharp edges, as you can see in the pictures, as well as many areas for people's arms, legs to get stuck. As you can see in the bottom left corner over there, that is the current foot pedal, leg. The leg currently stands in the raceway of the riders, which is very dangerous when wind loads apply and can tip over the fence as well as hurt the riders while they're racing. So some of the problems that were noticed. This slide summarizes what's wrong with the current fencing system. The existing fence weren't designed for these high-speed races. The sharp edges and big gaps are areas where riders can get snagged and caught up, causing serious injuries. The panels can even tip over, which can cause even larger injuries when riders fall into them. Because of that, we decided to design a new race barrier for our client, which reduces entanglement, absorbs impact, stays lightweight and easy to set up as well as for transport. So kind of our project goal and scope. So first we're going to design a barrier specifically for the Tour of America Dairyland races. Then we're going to use some FEA to check some stiffness, strength, as well as deflection under rider impact, as well as wind loads. Then we're going to compare materials such as steel, aluminum, plastics, as well as maybe combining all of them together to kind of make the perfect design. Finally, we're going to deliver a barrier concept to our client that satisfies or even exceeds what some of the constraints that are set.
So background research is a big part of the senior design elements or projects, and pretty quickly into our background research, we realized that there hasn't been any real research around fencing in cycling races. There are very few products that are designed specifically for cycling fencing. There is no research that has went into how to make these fences safer for cycling. The only research that we found was a paper that generally stated that you can crash during cycling races, which is pretty obvious. And when we were looking into some of the standards or constraints that we might have to apply, the different codes that might exist, we found that there aren't any codes that really exist around the cycling fencing products. And so for our design, we wanted to exist some of the design philosophies from existing fences that are used in other sports, possibly integrate some future constraints that we might see if any governing bodies ever do have any fencing guidelines, and wanted to make sure that all of our clients' wishes are incorporated into our design. So looking at some of the standards that might exist, there are 3 governing bodies that we're going to be looking at. There is the UCI, which is the international governing body. They
do not have any codes or standards right now, but they have said that they are looking into possibly making some in the near future. There is USA Cycling, which is the governing body for Toad. So if they have any standards, Toad would need to be following their standards for fencing. But at the moment, they do not have any set requirements. And on their page, they only suggest that you should have barriers at some point on the course. And then obviously, we want to be making sure that we meet all of the design specifications that Toad is asking us to have in our fencing design. So 3 different kind of designs that we saw that we wanted to implement some things from. This first design is from 1995. It was one of the first crowd control barriers for sporting events. It's portable. It keeps the spectators and the athletes a good distance away from each other, and you are able to fill it with liquid to make sure it's weighted, but this is a pretty poor design. It takes up a larger volume, so it would be very hard to transport, and it was made out of wood, which is not the best material for these events. The second design here is a newer design. This is a newer general sporting fence. It's made out of a high density plastic that is blow molded so that once you have the mold, you are able to make a lot of them. It's weather resistant and UV resistant. It's not metal, which is good, but the feet are in poor positions and it's very hard to weigh these down. So these would be flying all over the place in the Midwestern winds that we get. And then finally, a product that just came out recently is the Bobland Sport Barrier. This is a cycling specific barrier that was just made by a Belgian company, Bobland. There is no barrier on the race course so that the riders do not have to fear riding into the barrier at any point. And it was specifically designed for cycling, but it was more so the European stage race kind of cycling that you'd see in Europe, like the Tour de France. There are extra steps that you need to take when setting these barriers up. They are very hard to weigh down, and they are a very expensive product that are outside of the range that Toad is looking for.
So to go over the key requirements, the constraints one more time. For the safety requirements, we want the fences to be high-speed impact capable. They shall be stable under wind. They shall have small openings so no limbs get caught into the fences. We want to have round edges so that they are safe to touch by either spectators and by, as well as the people setting up the fences and the riders as well. Then for logistics usability, we want the barriers to have a low overall weight. We want to have a small footprint so that it's nice to stack and store when it's not used in races. And we want to make the clients to be able to set up the fence for about 328 feet of fencing in about 20 minutes. For the longevity, we're aiming for a 10-year service life for the fences, and we want to keep the material fabrication costs on the prototype budget as low as possible. To more emphasize on the importance of the product development approach in our project, we made ourselves a plan and a project development approach that can help us with finding the best solution possible. To do so, we first separated all the functions of a fence into sub-functions. So we basically took all the separate small little things that a fence has to do and gave them a little word, a little sentence, which I will show you in a moment. And each of this sub-function will get partial solutions. So we find partial solutions for all of these sub-functions. We then will combine them in the morphological metrics to get an overview over all the partial solutions. Then we'll have to check for the compatibility of all of these partial solutions to see if there are some variants that will not go together. At the end, we were able to create a solution tree to see all of the solutions and design paths that we can take for the final solutions, which was then used for the designs and for the down selections on our final design. So on this one, we can see now the morphological metrics. You do not have to spend too much time reading the right side, the partial solutions. I will not go over them too much because we don't have the time for that, sadly. But on the left, you can see all of the subtext fragments that we created for the fence. So first of all, the fence has to be able to stand up. Then it has to cushion the rider on impact so that they don't get hurt. The fence has to be prevented from tipping over. It has to be able to display sponsoring signs. It has to withstand the forces from the wind. It has to make the fence's footprint. It has to be small. And we also want to make the fences easy to be carryable. To kind of give you an idea on how we use this is the current fence design evaluated in our morphological matrix. So you have the centered feet at the bottom. You can weight the fence because you can put cinder blocks or sandbags on the feet. We have implemented holes into the design so that the wind can pass through the fence itself. It has generally a flat design, can be pushed together to be stored away, and it can be carried by the rails, so kind of like carry handles. It currently lacks any cushioning for the rider. We're not going over the compatibility matrix in itself because it will also take up too much time, but the key points that we noticed were that 3 of the solutions we discarded entirely, 3 of the partial solutions. First of all, were the slide and feed, which we noticed when we were talking to you, our client, because you pointed out that in general, this design is, first of all, too complicated and also too expensive to manufacture, which we agreed on, which is why we discarded this solution entirely. Secondly, to add padding on top of the fencing, we'll get rid of all of the solutions that we have for implementing sponsoring signs onto the fence. And lastly, adding wheels to a fence will increase the footprint of a fence in an inefficient way. Also why we discarded that solution. So what we came up with then is that we had 8 total concepts, 2 made by each of our team members. And we had different design variations and partial solutions for different fences so that we can take all of the good things from this and place our down selection out on this for the final design. The first of which is the one from Logan.
So for my design, I want to keep it as simple as possible while also making it easy to set up and take down. And for mine, I just have a simple front panel with 2-inch holes, as well as a back leg assembly, which just uses standard ladder spreaders that you get off the shelf. This can be set up in a couple seconds and also take down in about the same amount of time. And it was relatively inexpensive. That's why I went with this design for my initial proposition.
So as you can see on the board, this is my design. So some of the things that I kind of focused on were getting rid of those big gaps as well as sharp edges. So when you look at the design, you can see a lot of rounded edges. So the front face is 1-inch perforated holes over it, allowing it for airflow. The top, instead of having a sharp edge, is a rounded top, allowing for kind of the curvature and preventing injury when you fall into it. Kind of focusing on the legs, you can see that they have holes within them, allowing for sandbags or masonry block to be placed in the case of extreme winds and the fear of tipping over. As well as you can see that it's on an angle. So typically when the fence is on an angle, it allows for the cushioning of the rider. So I kind of focused on that as well.
So for my solution, I went more on an approach to create a modular design. My focus mostly was on the fact that I wanted to create a design where you can connect a complete fence line in an easy way. Generally, that was most of the pro points out of my designs. The rest was deemed also by the client as too cost intensive and also a little too complicated for the use case of that.
Finally, for my design, I wanted to make sure that the design would be able to be used in as many scenarios as possible. So there is the ability to rotate the angle that the fence face is at, depending on where you want it to have. The ability to possibly incorporate the already existing fences by just plugging them in where this fence face is standing, and as well having a base plate that goes into where the spectators are at so that the spectators themselves can act as the weight of the fence instead of needing to put down sandbags and cinder blocks in every fence.
The reason why we showed you exactly these 4 solutions is that after we created these designs, each of us valued and evaluated all of the 8 designs to create kind of a metrics to see which of the designs is the most possible to pursue and the most good design overall. So in the direction we presented them, the one from Logan was deemed the best solution so far. Then there came the one from Jacob and the one from me. But also, since we found also things that we would like to implement from Charles' design, we also used that to create our overall and final design.
For our final design, we ended up combining different aspects of each of our fences. Some of the points that we deemed that we wanted to keep in our design is a low weight, the swing profile, and the easy setup and transportation of the fences. Some of the aspects that the Toad team pointed out from our designs that they wanted to make sure were in our final design is the rounded edges, the foot plates. They wanted to make sure that the fence was vertical. We didn't need an angled fence, and that perforation was good and the fence was foldable and easy to have in a small footprint.
Moving on to our final design, I actually made a prototype of it. As you can see here, it's actually quite easy to set up. You just fold out the legs and stand it up, and then you put down the foot pedal as well. It would be as simple as that to set up in the final version. It took about a couple seconds to set up, and it would also take about the same amount of time to put back down. Just do that, and you would be able to stack them on top of each other on a cart of some kind to roll around to wherever you need to go.
Is this a scaled version or is this the
And
actual?
that's a 1/3 scale version. And moving on to the exploded view, this is how it would be more manufactured on a full size version. You would have 2 sheets of plastic that would be that would sandwich the steel frame that would give it some rigidity. And then we have the hinges here. If you can see here, there's actually pins here, which would allow the legs to be removable if they ever got damaged in any way. So you wouldn't have to replace the whole thing. You would only need to replace the legs. As well as there's only 4 bolts connecting to the foot pedal. So if you feel like you ever don't need that in any given scenario, it's very easy to remove, or you cannot even have it there entirely. And then going on to the next one.
So kind of the FEA and how we came about. So FEA, finite element analysis, we pretty much wanted to simulate a person crashing into this fence, as well as the wind loads, as well as multiple people. So we ran loads with 3 people as well as 5, so a full pile up. The way we went about this is pretty much we had the SolidWorks model. So this whole fence was modeled in SolidWorks. We imported it and allowed pretty much a dummy load. We did 3 PSI onto the panel. This allowed us to calculate the deflection from the panel. So pretty much the movement that will occur when someone hits it, kind of the kinetic energy absorption that it has. From there, we were able to calculate a K value for stiffness, as well as reverse into another equation, getting the overall deflection for the material. From there, we were able to apply a load for the actual amount that we wanted. So we ran a 200-pound rider with an 18-pound bike. Pretty much from there, we were able to gather the force on the panel as well as the deflection. We were also gathering from there the reaction forces that were occurring at each of the legs, as you can see there. So on that image, you're able to notice the deflection, so kind of the movement. And the max deflection occurs at 0.87 inches. I will dive a little bit deeper into that. So the FEA results when we ran them showed us that the panel handles the force fantastically, having a positive margin of safety. The leg region is our limiting factor. So one thing that I do want to address is that when we were running these loads, we constrained the leg. So pretty much, if you want to visualize it, it was either bolted to the ground or pretty much glued. So it wasn't able to move. That kind of shows the large deflection that occurs, which is unrealistic for real application due to the sliding that would occur when someone impacts the fence. So that's one of the things that we'd like to mention with the FEA.
And then moving on to the semester 2 plan. In the weeks 1 through 3, we want to confirm the requirements for our final design, as also create a design for manufacturing. In the weeks 3 through 6, we want to have CAD refinements and then also have final validation of the FEA. And in weeks 5 through 7, we want to create a final bill of materials, the final cost estimate, as well as get supplier quotes to know what it would cost to manufacture it at larger scale. And then in weeks 6 through 8, we want to acquire the materials to make the prototype, as well as make some manufacturing drawings. And in weeks 7 through 11, we want to create the prototype as well as start assembling it. And weeks 11 through 13, we want to do testing on that prototype, as well as validate that it will survive the loads in a hopefully long-term scenario. As well as in weeks 13 through 15, we'll do the final documentation and another presentation. This is just a visual version of what I just stated. There's a lot of overlap in there, just in case if things take longer than needed, because we don't fully know yet. But that's all I really got to say about this slide. And then moving on to the budget. The budget was split into 2 parts. First part was the barrier materials themselves, and then the manufacturing costs for the prototype. The goal was to build one functional prototype at a reasonable cost by the end of the next semester. We would leverage school resources such as the tools, the welders, and 3D printers to reduce the expenses. And then we want to also include a 10 to 15% cost buffer for waste, any rework that might be needed, as well as the shipping costs. Here's the actual price for the prototype itself. The cost came out to about $624. This is, a lot of it has to do with the price of McMaster. It's quite expensive, as well as the ABS plastic sheeting itself. It's possible to create the design with only one plastic sheet instead of two, which would reduce the cost by about $70. And if we also deem that the foot pedal is not worth it for the cost, that would also reduce it by another $115 about. And then moving on to the manufacturing cost of the prototype, it's quite a bit cheaper at only about $80. This is due to us being able to use the welders and tools that are on campus already. The only thing that we might need is a heat gun to form the ABS and any clamps to form any jigs that we might need. But beyond that, there's not really much to go on for the manufacturing costs.
So for the conclusion and the recommendation, throughout this first term, we created a design that finds a balance between our client's needs and the criteria that were set by us and the client. Then the new design itself offers transportation, modularity, and a reduced risk of injury. And for the next semester, we want to find a feasible method to manufacture the fence and to make it cost efficient. These are some of the sources that we have used. Thank you very much. If there are any questions, please let us know.
Okay, let's move to Q&A. Industry sponsors first, and then committee members, and then general audience. Questions from industry folk.
Question, the holes, the size of the holes in the fence.
2 inches.
So I noted that, but my question is, how do you determine sort of the, for the ultimate, the best, you know, we're talking about something where if it's taking on wind, we don't really want it to blow across the street or over current solid designs. If they've got signs on them or something like that, that's what they'll do. You know, weighting, we're using sandbags, we're using cement blocks, you know, a variety of different things to weight them. Sometimes people help, but you can't always count on. You think about thousands of feet of fencing that we might use on a race course. There's somewhere there might be a lot of people around, and somewhere there's going to be no one around at all. So we don't want people to be able to put their hand through there. But does that tells me is like, okay, my fist is bigger than 2 inches. Is there a through science or whatever and wind forces an ultimate, like one seems to be overly too small, so I see 1 to 2 inches, but could it be 3 inches? Could it be 4 inches? Could it be, I mean, the answer of course would be, it could be anything you want it to be.
Yeah.
And we know right now that we've got just some structural support that goes through there. So you can put body parts through there at ease, really. Anything can go through there, whole body can go through there. So how do you find that sort of the right median to really land on?
So I can kind of talk about that. So we began with the 1-inch holes. So there is an internal framing that we're using inside of the barrier in order to withstand the loads of the rider. So pretty much there is equations that we can run for wind load. The way we approached it was we wanted to fit as much holes as we could with that internal framing, as well as kind of cover the most surface area, allowing for that airflow to come through. So we noticed that there was a lot of surface area open with the 1 inches. We bumped it up as well as allowed fillets for the holes in order to kind of guide the air through it better. That's definitely something that we can look into. The approach that we have right now allows a really good amount of airflow through it.
There's also a possibility to alternate the way that the holes are arranged. So on our current one, they're just like stacked right on top of each other, nice and evenly. Right. You can actually just alternate it into the center. That would allow more holes to be created and less gap in between if we've deemed it absolutely necessary, while not really hindering the ability of the plastic to maintain structural support.
Sure.
We also, we know that we use sandbags or masonry block. We also noticed that you enjoyed the foot pedal. That could be also a really good situation where the crowds are helping support the barrier.
Yeah, I think it's like where we know there's going to be crowds, it's less cinder blocks. If we know that we're gonna have fenced out and there's not gonna be nobody there, it's more cinder blocks or more sandbags to support it. So with the material, would the end goal be to get a mold and then injection mold it? I think that's what it's called. Is that right? And is that what the end goal would be to manufacture the fence then, or is it using materials that are already available and working with materials that are already available?
It would be, the goal would be to either make the design like injection molded, like you were saying, or have just one sheet of plastic so that you just like mount it to the front of like the steel frame. So that would be very easy to assemble and like also very cheap to make. Because it would be very expensive to make that injection molded, because you have to make the mold at the size of the actual frame, which would be like a 4x8.
Yeah.
Which would be really expensive.
So yeah, it's a quantity question. So there are different processes, injection molding. We can just get a piece of plastic and just cut the holes ourselves.
Right.
That's kind of the approach that we're going for the prototyping. But if you're asking for hundreds or thousands of these fences, having the initial cost of making the mold might be up there, but it's gonna increase the time as well as save you piece by piece if that's the approach.
Yeah, I mean, and I think that the end goal would be thousands of pieces of fencing eventually. I mean, when it makes it, we've got, counterparts all over the country who are looking for something safer.
Yeah, agreed. I think like the final design, whatever you present, should be with the intent of making thousands, right? Talking about a prototype that you can build yourself to demonstrate the purpose is one thing, right?
Yes.
But when you present the final design, you should present it in a way that you can make 1,000.
Yes.
Is that clear?
Yes.
Okay. Better? Yeah. I have a few questions, if you don't mind. So when you stand it up, it's basically kind of like this very vertical orientation. You might just put it up there real quick. It's got like this vertical orientation. So is the plan to always have some weight on the, like those legs that kind of come back towards me?
Yes.
Like always?
Yeah, we would just assume that there would always just be some sort of sandbag or something.
And is the weight like humans in some case, or does every single one need to be sandbagged?
Every single one most likely would be sandbagged.
Is that a problem for you?
Well, I don't know. Let's say it would be a challenge.
Yeah, it's a bit annoying, right? To have to do you have to counterweight every single one of these.
Well, current situation is we have, as you've seen in the pictures, the feet are, I don't know how, they 2 feet long, maybe?
Yeah.
2 feet long, the attachments in the middle. So they're freestanding, they're not gonna really go anywhere, even in a reasonable windy day, if it's just the fence with no signage on it, it's not gonna go anywhere, it's very stable.
Sure.
My concern about a design like that without anything on the front end of it is that how easy is it for that thing gonna be? And if it's gonna go anywhere, it's gonna go
into the race.
or it's not gonna go backwards. Now, let's remember also that this is crowd control barriers, so
Exactly. So
we're not generally putting it in the race course. It's usually up off the curb. in a grassy area.
What's a crowd member gonna do when they walk to a barrier? What does every crowd member do? They lean.
Lean on it.
Of course.
Right.
So
When they lean on this design, they're pretty much leaning on their own weight. So if someone walks in close to the barrier, they're stepping on that foot pedal, and then when they lean, they're pretty much leaning against themselves.
right, but that also needs to be something that you do in FEA, because let's say somebody's standing on these planks, let's call them, that are kind of on the closest side to me. And then you're leaning on the top here, that's huge stress on the base, the base of the cantilever here. So that needs to be something that you think about, right?
And I would say, so, we don't like it, with the feet that we have, people definitely do ride over it, but their handlebars are almost wide enough that like, if their wheels hitting the base, that their handlebars are hitting it, so it doesn't happen a lot. That putting a front support that folds down, as long as it's flat to the ground like our current ones are, is not unreasonable. If it has to be out in the road to counterbalance that force that's going forward.
I think even if it's just a couple inches can be very helpful. 1 2
Yeah.
inches can be really helpful.
Absolutely. The only reason we kind of steered away from that design is you guys mentioned that there was situations
Yeah.
where the barriers fell over and then it's pretty much turned into kind of like a knife slash dagger for anyone riding into it. So we tried to create something that kind of eliminated that, but definitely something that we can implement in our.
And what's the idea for the material for the foot plate and the feet or the?
It would just be steel box.
Steel.
It would be use the material from your current barriers and just re-implement them by cutting them apart.
One last question is about modularity. I think Bjorn, when you presented yours, you talked about the idea of like linking them together and modularity. I think that's something that's like attractive to you guys generally. Have you considered that at all in your design? Maybe like hook here, so that you can
So
do this sort of thing, or are we kind of trying to get away from that? I guess.
We have another beautiful design that came out of MSOE
Okay.
for connectors.
Yeah, sure. It's true.
So you could build it into the fences together, but I mean, the other part of it is there are times when you want that link to break.
Right.
And not break not necessarily in a damaging way, just you want to be able to get it apart quickly to access a crash. Emergency vehicles are coming on the course, you need to create an opening, or if there's a impact, as we saw from the video from the previous group, which was shot in Shorewood, somebody hit a fence and everything was well attached. And there was this domino effect of pieces of fence going down, and then this scene of the fence feet going up in the air like this, which is almost a worst case scenario of somebody being impaled by one of those.
Yeah.
One of those.
Well, maybe this isn't back and forth you can have it then, but you could even design almost an explosive bolt. It's not exactly what you want, but something that is purposely designed to fail in the case of a super high impact or them tipping over, right? So
Yeah.
a link that is kind of weak by design in case you have a sudden impact, it breaks away a little bit.
Yeah, it's almost, I mean, in some ways, it reminds me of like the airbag in a car, right? It's gonna stay together under normal conditions, and when there's an extraordinary event. Yeah.
absolutely.
Okay. Well, we got to move on. So thank you for the presentation. A lot of good stuff here. So thank you. Okay. Sorry about the change over time. It's 2:31, so. I get one bite of apple. I think so. Yeah, green light, whenever you're ready. Take it away. Go ahead.
All right, good afternoon. Thank you for coming. Today we'll be presenting on our tour of America Dairyland bike barrier padding. My name is Luke Langier.
I'm Seth Thomas.
And my name is Michael Stoller.
All right, so for some race safety background, competitive racing has been going on for over 150 years, with approximately 3,000 cycling events happening annually worldwide. As local as Tour of America's Dairyland that happens right here in Wisconsin each year with, and they host approximately 500 riders a day. And so big races like this, it's inevitable that crashes are going to happen. And cyclingnews.com partnered with the university in Belgium to analyze a bunch of crashes that happened during bicycle races that resulted in hospitalization injuries. And they found 497 crashes, and 35% of those were rider-related error. Another 13% were course setup related. So that could have been densely populated areas, tight turns, or when bikers are going into the straightaway. And so although bike organizations are doing a better job nowadays of trying to create, rules about course dimensions and safety layouts, they're still going to happen. They're inevitable. And with the existing fence design that Toad has, riders can still get cut on the sharp corners. They can have limbs that go through the large gaps, which can injure themselves or the spectators on the other side of the fence. So the first part of the project is identifying the problem and figuring out what we're trying to solve. So Toad made it very clear that they want us, our team, to work with the existing barrier fence. So we're not going to be fabricating and manufacturing a new solution to replace that fence like the other group mentioned that they're going to be doing. So we're going to be working within this design, creating some type of solution to fill those gaps, find some type of solution that's got, that has some way to have airflow go through it. So it's not going to, so the wind is going to be knocking it into the course. The last group they mentioned how that's still a big problem. Same thing here. It's also going to have some type of structural integrity. We want to have an estimated lifespan of over a decade. So it's, worth the investment, and it's also got to be within the budget of about $20 per linear foot.
There are a lot of project goals within the project itself. It's kind of split into two phases. The first 15 weeks of the semester being phase one, which is where we're going to create and evaluate the general 3 design concepts that we came up with based on the feedback from the Toad team. Phase two for the second semester for the next 15 weeks, that will be the fabrication and testing phase, where that's where we take the selected design approved by the Toad team and then build and test the selected concept to just validate any performance assumptions that we may have. The final deliverable will hopefully be a functional pattern design ready for race day deployment or mass manufacturing. Speaking with the Toad team, we wanted to make sure that we got all the stakeholder needs out of the way, ensuring that the needs they wanted for the race made it as optimal as possible. So we got the best pattern design. One thing that we talked about big with the Toad team is enhancing the general safety of the actual events itself. So for rider barrier impacts, we wanted to make sure that we designed something that had a lot of, that reduced the injury risk for the riders itself, blocking the holes and ensuring that their limbs won't get caught into it during the crash. The next one is going to be the general operational efficiency. We wanted to make sure with the small team that Toad has that they're able to take down and put up these barriers as fast as possible with minimal training, making sure they're pretty simple. We also wanted to make sure that they're easy for transportation for general race day operations, along with making sure that the minimal wind drag and they had a lightweight concept. The final one is going to be the general economic viability. We wanted to make sure that obviously they had a 10-year durable cost or 10-year durability, and then we had a cost-effective design. So anytime we had to replace the barrier, it wouldn't be, or the padding, it wouldn't be that expensive, staying within the budget of $20 per linear foot.
So with all the stakeholder needs out of the way, these are kind of the system requirements that the padding needs to fulfill. So one being impact performance. Padding needs to reduce impact forces and make the barriers safer for riders if they impact them. Structural integrity. So the padding needs to be able to be securely attached to the barrier. It falling off the barrier renders it useless, renders the barrier useless, and it needs to be able to stay on under wind loads and impact loads. Aerodynamic efficiency, just like we talked about, padding cannot increase drag forces on the barrier, causing it to fall over when it shouldn't, because this makes the barrier even more dangerous. Then manufacturing feasibility, like we said, hundreds, thousands of these are going to be made. So it needs to be able to be made on a mass production scale, be cheap enough and easy enough to do that with. So after identifying all these needs, we went to identify the state of the art and do background research to see how we can make design concepts. So we obviously checked out materials, which can reduce impact forces, as we can find materials that we can use for our padding. We also looked into some netting solutions, like for trampolines, because they can, increase the length of that impact to make it a lot safer. Also looked at certain porous structures to reduce drag forces on plate surfaces. Then we also looked at hardness for materials to check out which materials or which combination of materials we could use that which has the right rigidity, flexibility that we want in our padding.
So for the first design formulation that I came up with was this padded sleeve concept, which was made out of some PVC mesh screen material that you can often see on the outside of construction sites. There's some actually right outside that window right there. And they'll often put that on the outside of those chain link fences, and it can allow some airflow through it. And then for the CAD picture, the yellow, that would be some outdoor sports padding that you would see at recreational baseball fields or football fields. And so an advantage of this design is that we know that it's proven to have some airflow that goes through that mesh vinyl screening, as well as the padding is protective. It can absorb impacts. But a big disadvantage to this concept was it was very over budget, very expensive with those custom padding dimensions that was going to cost this design a lot.
For the design that I came up with, I wanted to try to keep everything really simple. It's very similar to any sort of padding you'll see in a gymnasium, that the paddings may be against the wall. With the redesign that I came up with, I have improved airflow with holes that are around 1.5 inches. The design that you can see on the right is going to be for half a fence with a split in the middle that includes the vinyl coated polyester, so that the padding itself would be able to fold over itself for easy transportation. There's a lot of space for advertisement, as you can see, and then there's also generally increased protection for the use of the padding I designed for the polyfoam. The barrier or the padding itself is very easily attachable. It uses 4 aluminum U-hooks. As you can see in the top right here, these 4 connections make it easy to actually attach the barrier onto the fence itself. And then the design I came up with is also very budget friendly, with the plywood or weathered plywood being marine grade, being around $25 to $40. The polyfoam itself is around $30 for the 34 by 35 dimension. The aluminum U-hooks, depending on where you get them, are going to be around $20 to $30. And then the vinyl coated polyester, which is just on there for increased protection for any weathering, debris, or sweat that may be in contact with the padding itself, increasing the durability over time. The total design that I came up with comes out to around $170 per fence.
So then this design concept is kind of inspired by those trampoline nettings that we looked at before in our background research. This one, as you can see here, would kind of have this scoop design where it would have some sort of poles which would stretch out from the barrier and have the net scoop down so it can like catch riders before they hit the barrier, so not impacting the metal right away. Also, it being a netting design, meaning it won't have any like drag forces adding to the barrier, so it won't make the barrier fall over in the wind. Issues with the design though is that it has to change the barrier in some way. You know, adding stuff to the barrier is not really in the scope of this project, so that would be one of the big disadvantages of this design.
The next step was to create a trade-off study matrix grading each of our designs. We came up with a list of categories to grade each design with. So some of them were price, manufacturability, safety, time to set up, transportation, etc. And then we weighted each category based on how important we thought it was that our final solution would have good scoring. So safety, aerodynamic efficiency were weighted the highest at 20%. We weighted them the highest because they're the most brought up in our prompt statement, and Toad was most concerned about that when introducing the project to us. So we each individually graded each design on a scale of 0 to 4, 0 being the worst, 4 being the best, and then we averaged them out and we got this final table. You can see that design 4, 6, and 2 were our top 3 designs, and then we presented them back to Andrew and Bill, and we got their constructive feedback, and then we put our heads together and we decided that we can do a better job of coming up with a design that kind of gets rid of all the disadvantages of the proposed designs, and we used the advantages and we've combined them together. So we went back to the drawing board and we're looking for materials that we could use or to get inspiration off of. And we found this Corite material. That's a very brand new material, new technology that's being put into bike helmets, ski helmets, and it's known for its tubular structure and how it can collapse on impact. And so it's known to be 95% air, which is exactly what we're looking for as far as airflow. And what it's known for is that when there's like an impact, it uses 78% of its material's thickness to absorb that impact, whereas typical foams that are used in bike helmets and ski helmets they use 60%. And so when this absorbs some impact, it can shrink down to 78%, but it also regrows back to almost 100% of its initial height. So it's able to take on multiple impacts without replacing the helmet, whereas typical foam helmet, or that typical helmets that use just regular EPS foams, and they shrink that 60%. Typically, they stay at that 60%, and you need to replace the helmet right away. So using using that chloride material, we were inspired to create some type of honeycomb structure into our final design. And this structure would be throughout the entire design. We couldn't implement it into the SolidWorks design because of how small these are and how big the actual barrier is. But we would plan on using a fiberglass polymer composite material for its lightweight and its strength. We'd manufacture it by using some type of vacuum barb process, or to test it at least. Once we would go into large scale manufacturing, we'd probably end up creating some type of mold to be able to produce this at a large scale. We added some fillets to the exterior to prevent some of those sharp edges that the existing barrier had. And then we also added perimeter holes for advertisement mounting. And a huge advantage too of using a fiberglass polymer composite is the price. So it's well within budget, and exactly what we're looking for. We also wanted to get some evidence to prove that the honeycomb structure actually works with some finite element analysis. So we just took a 13 by 13 by 2 3/8 inch sample of what the honeycomb structure would look like. We applied a very conservative 400 PSI force to it, just to simulate a worst case scenario localized crash on the structure. And we ran a maximum von Mises stress as well as a deformation stress. And we got 6,885 PSI for the stress. You can see how well it was able to distribute that load across the model. And then the deformation was 0.0017, which is also a great number to have for the deflection, pretty small number. And yeah.
So then we also have another design which focuses more on covering the barrier and less so on padding the metal itself. This barrier is inspired, kind of an evolution of the netting design, which we had before. As mentioned, it had to add stuff to the barrier. This one instead would have no modifications to the barrier, would just be able to clip onto the barrier using carabiners or some sort of easy metal clip, keep it easy to put on. And then for the bottom, it would attach to the bottom of the feet. So it still has some of that scoop shape to try and get space between the net and the barrier so it can cushion riders a bit. That would be connected using U-bolts or clamps, a lot of super cheap, easy ways to do that, which don't take a lot of time to set up. Again, no barrier modification. Nets are easy to transport, super lightweight, will not catch the wind at all, is cheap and durable. A lot of nylon or Kevlar nets can easily last up to 10 years and have a lot of tensile strength, and has more focus on covering the barrier, not allowing limbs to get through the barrier, while having a little bit less of that impact reduction as the other design.
For the second semester in phase 2, we plan on doing a general impact and wind test. With the actual design itself, we want to do a drop tower test, taking the sample itself and then testing the deformation based on a given load. We'll also do a general fatigue evaluation, as we want this padding to last up to 10 years. We're going to do a multi-impact test to just assess the general material durability and long-term performance. We'll do a wind tunnel test, as we don't have access to actual wind tunnels. We do have access to industrial fans, so we will use industrial fans to just test the general drag, oscillatory patterns based on the gust response characteristics of wind blowing into the fence with the padding on top of it, making sure that the padding won't cause the fence to fall over into the race pad. And then we also have the general assembly verification, ensuring that the padding itself is able to put on and take off. And the setup is going to be very short, and the deployment is very reliable. The general budget for the final design for 1A is going to be around $178.64 per unit. The general cost is minimized through the hexagonal patterns on the material design we chose, and then the actual design itself is based on the manufacturing is going to be very stable.
So for the feasibility study, the biggest challenge for this is getting this design made for hundreds, thousands of these. So getting manufacturing processes figured out, finding manufacturers that can do this hexagonal structure that we have and create molds or do something like that to get the manufacturability up to par what it needs to be so it can be made on a large scale. Then with aerodynamics, with the wind test, we can validate that it doesn't knock the barriers over, that it allows flow to pass through. And with impact performance, like drop tests, we can validate that the padding actually reduces impacts and makes the race safer for riders.
In general, the Colroyd and netting design both meet all safety requirements based on the given criteria from the tow team, and they meet them very effectively. In terms of manufacturing, the designs themselves are highly manufacturable with general simple deployment. And the next steps for semester 2 will just be testing and the actual full-scale model building of the actual padding designs. Thank you.
All right, got some time for questions? Industry first.
First, I like both of these designs a lot. I like that Colroyd thing. It's very, very cool. The second design question, so the sort of scooping out at the very bottom of it, is there some, what's your perceived benefit of having that? I mean, I can see on an angle basis that it, creates sort of a nice falling space, but if it's only bending out at the bottom and if it's adding cost to do that, what's the return on that part of the design?
So the thought process behind that was like, if you think of like a trampoline netting, it needs some sort of deflection, needs to be able to stretch and deform in order for it to stretch out the impact and make it safer. Then it was just like clipped to the fence. It would basically just be covering the holes and wouldn't really provide a whole lot of protection against the metal. By giving it a bit of space for it to deform when riders hit it, it would also be tension so that it would be stretched, so it would have kind of this like rebound and elasticity effect, and it wouldn't really add any cost to attach it to the feet rather than the bottom of the barrier. I mean, those clamps and U-bolts are super cheap, and making a solution for that is not going to add a lot of cost to the design. So that was kind of the thought process behind it, is give space so that the net can deform and reduce the impact forces that riders have when they hit the barrier.
Yeah, it would take a lot of time for us to do that on a piece by piece basis on race day. Would be probably the biggest hindrance or something like that. What's the material proposed to be made of it?
So there's like a lot of the pricing that I had was based off of it was like a nylon netting for sports applications. So this is like, they use it in like soccer nets, or I mean, it's in a lot of sports applications. I think I was looking at tensile strengths can go anywhere from like 285 pounds to like 480. There's a wide range of costs and like abilities for this net. So it's kind of variable. We can test that out to see which best suits the application. But
is that kind of material printable, would you think? Could you print like sponsor names on that kind of stuff? And could you buy it in, you think you could buy it in rolls? Like the scrim that we use now is really, it's really tight though. So it's okay in windy conditions, but it's not great. So if you add that, which comes along this, but with larger holes in it, and you can still print it, then you're accomplishing a bunch of different goals at one time.
Yeah, with the material research that I found on the exact same netting, they are available in large rolls. So the actual quantity itself, it would actually decrease in price for the that you actually buy.
Yeah.
How dependent is it on the fence being perfect to do this design though? Like if a foot is twisted just a half an inch, or is that going to take away from some of that tension and some of the springiness that would come from that?
I don't think that would really impact it too much, because I mean, it's going to have to be hand tension. Like, we're not going to have like clamps or anything like that, because that's, again, it's going to increase the amount of time it takes to put these things on. So I don't think the tension of like the feet being turned, I mean, because the barrier itself it's like 115 inches about. So I think it's long enough that, a turn in the foot wouldn't affect the tension of the entire fence over such a large area.
And with like the general requirements after the feedback we got, we found that you guys wanted to move more away from the actual padding of the fence and just more of the covering of the holes. So the actual turning of the foot itself wouldn't cause much problems in the actual covering that this netting design would actually provide.
Okay.
All right, committee. So I have questions. A lot of what you're doing here is about impact, right? I mean, you got these riders that are hitting this thing, okay? And the energy absorption can come from a couple of different things, right? When you think about like a spring energy comes from like the way the material is actually made and how it deforms when you bend it and compress it and things like that, right? So that really isn't necessarily, it's somewhat related to the material, but a spring stiffness is different from like the stiffness of steel. Okay, you understand what I'm saying? So you have two different ways that you're possibly trying to absorb the energy. One is with like this tautness of the net, more or less, that's going to absorb some energy. And then once that tautness gives, now you just have the compression of the material against the steel that's going to absorb some energy. Is that correct?
Yes.
Right.
So based on the given criteria, when we came back or we gathered the feedback after the design requirements, the idea was to move away from actually padding the fence, more so just actually covering the holes in the fence, stopping limbs from going through it. So that's why we have the actual netting design too as an option for less of an actual padding option, because they wanted to move towards more of covering just the fence itself, less than padding.
My question is, do you anticipate most of the impact absorption being from the net being tight or the material yielding? This is the question.
Like, are you talking about the net like tearing, like in terms of?
Well, in terms of impact, the idea wasn't to like stop the impact of or like protect the impact of riders itself. It was primarily to stop the riders' limbs from going through the fence. Based on the feedback we were given.
So you're not in any way trying to give additional impact energy absorption with the material, you're just trying to stop the limbs going through the holes?
Yeah, based on the feedback we got from the initial design submittal, it's just to stop the limbs of the riders from going through the holes.
Okay. So you're just, there's no care about softness or like damping, quote unquote, like for somebody hitting this?
It's kind of like, well, I can say like, that was probably one of our biggest challenges, I'd say this semester, is designing something that's like that in between. Cause like that first design that I had that like outdoor sports padding. I mean, even Seth had his gymnasium padding, and that's kind of the route that we were all looking at going. But then there was issues about like how that's going to handle with the wind. And so that, you're going to be able to absorb impacts a lot better with that type of material. But there's, with the wind, that's not an ideal situation. So then we had to go more routes about, all right, well, let's just make the existing barrier safer as far as making sure limbs aren't going through there, and kind of go that direction.
You mentioned some like impact testing next term then. So what's the point of the impact testing? If you you don't really care about the energy absorption or really care about that, all that you care about is stopping the limbs, why do you want to do impact testing?
The general impact testing was just based on the selected design that the tone team would like. So if they would like more of a padding design based on Luke's, we can do the impact testing to make sure that it does take them out of impact and lessens the energy absorption based on the rider crashing into the barrier. But we also do the general feasibility test where we do multiple impacts to make sure that the barrier actually, or the padding actually lasts over time.
Okay. Based on what I'm seeing from the current design, it doesn't look like you're giving a lot of help in terms of like absorbing the impact from the rider, right? Is all I'm saying. And if that's not important to you guys, then okay. But I think like if I'm considering putting some sort of cover or some sort of barrier over these things, you would at least want some impact absorption effects.
I think so. And I was going to just say, if I could defend the team a little bit here from the is that when we talked about it, so padding, I mean, pure padding, we put padding in high impact, potential impact zones. So you're coming out of a turn, okay? You come out of the turn, there's a certain area that's, if there's going to be, the majority of the crashes are going to happen there. So we'll take the existing fencing, some of it may have, you call it scrim on it, with a sponsor's name or something like that. And we'll cover that with these gym pads of essence. So we didn't really, so we sort of steered them away from creating something heavily padded because we already got an easy solution for that. And we can always buy more of those if we need them. But in really windy days, those things will flow over a lot easier because there's no airflow at all.
Sure.
So then you go downwind from that, I guess to say, similar to maybe, again, back to the video in Shorewood. And those areas are less prone to crashes, but they do happen.
Mhm.
So if you want that stuff to stay up in windy days and you're gonna have it out there for crowd control, where's that balance between padding it and paying the expense of padding it to protect the riders that do hit it versus creating a cover of sorts so that, you know, is it better to be padded and them hit it, or is it better that they not put a arm or a leg or a body part through it?
Mhm.
And what's the cost? What's the cost benefit and the risk ratio of that?
Yeah.
So that's kind of that fine tuned area where I don't know that I don't have a firm answer for what that would be, because there's, you know, at some point, there's only so much money that we have that we can spend on these things. So
I understand.
where's the best bang for the buck?
Yeah, and I would hope to think that if there was a netting, it would keep them from hitting the metal. It would keep the arms from going through, but then if there was some added bonus of not making it to the metal, because there's that gap that would spring back a little bit, I think that would be
Mhm.
beneficial.
There's, you know, the angled fencing on our start finish stretch. Oftentimes there are crashes on that start finish area, and like, okay, yes, the riders are gonna be injured. You know, there's no doubt about it. If you hit the fencing, something's gonna hurt, all right? We don't know how, to what degree. But having that angled fencing and have it covered with a board presents this sort of easy landing zone for the
Yep.
rider to go into. Then everything happens after that road rash. If he hits some, you know, it's not the fall that kills you, it's a sudden stop, the curb, whatever happens, then they've got some injury there. But we've prevented that catastrophic type of injury.
Sure.
And I think the same situation goes here where it's a balance. I think that Colroyd or whatever stuff is way cool. And maybe, you know, it's one of those things where we use this type of material in this part of the course, and we use this type of material in that part of the course. And then when we get to the big heavy crash zones, we put the padding over
Yeah.
that.
Yep, fair. Okay, we are at 3 o'clock, so we'll end the session here. Thank you. Good job.
Yeah.
Thank you. And that's it for the session. Thank you.
Thank you guys very much.
Appreciate it.
Thank you. All right.